Hopefully you can see my screen, right?
Yes, sir.
Yes.
Yes, sir.
Okay. Now, okay, so today we will see that fundamental group of circle is Z. That is the set of, that is the group of integers with plus, right? And also yesterday in the last lecture, one student asked that why if you have two loops in circle, if you go with one and if you go with twice, then why they are not homotopic. Today I also give the answer of that questions. But for that we need a concept of covering space. Okay, so I define covering space first. Covering, we need the concept of covering space. This is the first one. And also we need that path lifting. That sounds good, but actually that is not a difficult one. So what is a covering space and what is a path lifting? So first of all, I define what is a covering space. So let X be a topological space. Okay. Now a pair so X tilde and P, where X tilde is another topological space and P is a continuous function from X tilde to X. Okay, then this pair is called a covering space. See, covering space may not be unique. Okay, now a pair, that is a pair of a topological space and a map. Map means we generally call it is a continuous function, is called a covering space of the topological space X if it satisfies the following properties. So which property? If it satisfies the following property. Now the property is for each X belongs to X, that means if you choose any element from the topological space X, then there exists an open set U containing X such that, that's mean for each point we must have an open set containing X such that P inverse that U will be some disjoint union of U alpha, where what we can write it is because so by this notation this we generally call a disjoint union. Okay, that's when I write here disjoint union of open sets in X tilde, where if you take that P, okay, this is a map from X tilde to X. If you take restrict over say U alpha, then that U alpha to U is a homeomorphism. Okay. Now, if a pair, that is a pair of a topological space and a map satisfies this condition, then we will call that pair as a covering space of the topological space X. So is that clear, the definition of covering space? So that's mean actually what is, so I can take one example. It is better to say one example. Say by X is say circle S1, which we actually need, and say X tilde equal to say R. Okay, and say that my P R to S1 say defined by PS equal to cos 2 pi S comma sin 2 pi S in this way. Okay, so this means this is my X tilde. Okay, and we have a map. This is P and this is my circle S1. This is my X. Now if we take this point 1 0, now what will be the inverse image of 1 0 by the map P? As I told you, you should unmute and talk.
0, sir.
Only 0?
Yes,
Sir,
Every integer.
integers, all
yes, sir.
हाँ,
integers.
0
Integer.
भी होगा 1 भी होगा सब कुछ होगा हाँ 0 से 1 से 2 से 3 -1 भी होगा है ना -2 -3 everything if you take inverse image of that. Now tell me, if we take an open set say containing the 0 small open set, then what will be the inverse image of that open set?
Like it will be union of open sets containing integers.
Right, so it will be this kind of, right? All of this, right? Is that clear? If you take this u, then you will have some u0, you will have some u1, u2, say u minus 1, u minus 2 in this way. Right? And you can say that by that map P, if we take any ui, then that ui to u is a homeomorphism. Is that clear?
Yes, sir.
Because see, by what is that map? If we take s equal to 0, you get 1 0. If you take s equal to say 1, that means 0 to 1, it will round 1, right? It will just round 1 and it will come back here. Now, suppose if you take this kind of say open set, now what will be the inverse image of this kind of open set? It will be something kind of this kind of open set.
Half integers.
Right, so this kind of. Right? Now, is that clear actually to you? So now what is the definition of covering space? So if you have a topological space, then covering space means you have a this kind of pair.
No, but like, what's the motivation for this?
That
Like,
covering
why?
space,
Yeah, like this example is clear. The definition also I understand, but like, why do we define it this way?
that covering space.
Yes.
Yes, because we will see that application of that one, right? To prove that, I will give you that. Okay, right. After the lecture, I will give you the answer of your question. Because we need this concept to define, to prove that fundamental um, group of a circle is why it is Z actually. Okay, anyway, so first of all, anyone have doubt in this one? That is the concept of covering space. Anyone?
Sir, can you explain the homomorphism part again, like in this example? Um,
Right, no, right. So, but here you can check this is a homeomorphism because this is you can check it is the way we define that map P. It is actually see at 0, Mm. You have this line, say 0, say 1, say 2 in this way, right? And you have a circle. Okay. Now, whenever you have 0, then this point is 0. Now it's going to this direction, it will move to this direction. And when you reach 1, it will goes to 1. Okay. And again, when again you passed 1, then again it goes in this direction, and again it will move to, when it is 2, then it is moved to 2. Okay, so that's mean if you consider a small neighborhood here, say this one, then it is a small neighborhood here as well. So this is just a, you can see that between open 0 1 or say closed 0 open 1, you can find that that map is 1 1, and obviously this is also 1 2, and as well as you can see that continuity also is it easy to check that P is continuous, and since it is 1 1 and 1 2, it has that inverse image as well between only say open 0 to 1, and then you can check that continuity of that one as well. Okay,
Yes, sir.
that is simple
Okay, and
one.
here, like in the definition for each point, we only need that there is at least one open set which satisfies that P inverse U is a union of
Exactly,
U alpha. Like
exactly. Not
so, we don't
not
need
every
that
all
every
open set.
open set containing it should satisfy this. No,
No,
like
no, no. It should not be. It should not be, because
but
if you
here
take
in this, like in this
uh,
circle example, like if you take X and you take any arbitrary open set U, then P inverse U is a disjoint union, and P restricted to any arbitrary element of that union is also a homeomorphism.
no, you can take
Uh,
that whole space,
if you take the whole
whole
space,
space, right?
yeah, then okay, if I take any arbitrary X and the whole space which contains it, and I take P inverse U,
It is
that will
actually
also be
it
the
is
whole space.
right, but that is not a homeomorphism.
Uh, no, I consider it as a disjoint union of a single open set, which is the entire space.
Right.
P inverse U is the entire real line,
Hmm.
which I consider it just as like just R. Basically, the
Right.
union has
Right.
only one set,
On set.
and now okay, now
But
it's
that
a homeomorphism because it's not 1 1.
right.
Okay, okay. Okay, yeah. Thanks.
Right. So yeah, but luckily here for any other open set, if you take, it will be a homeomorphism kind of thing. Right. But it is not generally true in general, because in general if you can have many more open sets which does not satisfy these properties. Okay. So for to define that covering space, we just need at least one kind of open set, one this kind of open set containing every point. So here for each point you need at least one open set which satisfies this property. Okay. And if you satisfy this property, then we have a special name for that one. Now if an open set containing X satisfies the above property, then we say U is an evenly covered neighborhood. Okay. So I generally write neighborhood by only NBD. Okay. So if I write NBD, you understand that it is neighborhood. Okay. So if you satisfy this property, then we will call U, that set open set U, as an evenly covered neighborhood. Okay. Fine.
Yes, sir.
Okay. Okay, now I can give actually answer of that question. So why do we need? What is the motivation behind that? What is the motivation actually? Now, if you consider a circle, okay, and if you choose one path, say which round only one, and if you choose another path which round twice, okay. So say one is F1 and one is F2. F1 is round once and F2 means round twice, right? And both have same endpoints because those are loops. So it is now how to say that F1 is not homotopic to F2. How to say that? Now what we will do actually, now we will prove that F1, for F1 we have some another path in X tilde, that is in the covering space. For F2 we have another path in again X tilde, say F1 tilde and F2 tilde. Okay, and then we prove that if F1 is homotopic to F2, then F1 tilde is also homotopic to F2. We will prove that. Okay, so that's mean if possible F1 and F2 are homotopic, then F1 tilde and F1 tilde both will be homotopic. But if you take round once, then its inverse path in X tilde will be say 0 to 1, this kind of path only, and another part, that is the lift of F2, it will be my F1 and F2 will be that range, it will be 0 to 2. And then we will show that that's mean F1 and F2 are not homotopic because they have different endpoints. Okay, to show that two loops in circle are not homotopic, we need the concept of covering space. So we will see actually so how we use that. So is that understood why we are using that? Yes. Who asked that question? Who asked that question?
Yeah, I had asked that
Ah,
the
right. So I'm giving you the answer. So why we are using
okay,
that?
right,
Okay.
right, right,
Okay. Because if we take one path once and another path twice, since they have same endpoints, so it is difficult to show that they are not homotopic.
right,
But
right.
but if we go in that X tilde, that is in the covering space,
Mhm.
then we will show that uniqueness, this thing we have to prove. And then we will see that if these are homotopic, then that F1 tilde and F2 tilde will be homotopic, but we will see that their range sets are different. So therefore it cannot be homotopic.
Okay, I see.
Okay, in this way actually we will prove.
Okay, okay, okay. Thank you.
Okay, now we will define that F tilde. Okay. Now this is called lift of a map. So we will not define lift of a loop, we will, of a path, we will just define lift of a map. Okay. Now first of all, let that x tilde p be a covering space of x. Okay. So we have a topological space X and we already take a covering space of the topological space X. Now we say that now let f y to x be a map. Map means from now onward, map means we say continuous function. Okay. And we define here the domain is any y. Okay, so we are not restricting our domain is only that closed interval 0, 1. It can be any space. So let A be a map and this is a covering space. So that's mean this is the situation. So this is my x tilde, this is my x and this is my y. So here you have map F. Here you have another map P which is coming from the covering space. Okay. Now another map, A map, that's mean a continuous function F tilde which is from y to x, okay, in this direction F tilde is called a lift of the map F if P compose F tilde equal to F. That's mean this map is actually commutative. So in this way. Okay. Did you get what is a lift of a map? So that's mean to define a lift of a map, you must need a covering space. So because okay, it is x tilde. Okay, so now if you have any map from a space y to a space x, and if you have a covering space, say x tilde, and if you have that map that x tilde to x, then a map f tilde from that y to x tilde is called a lift of the map if we have this condition. Okay, so in particular, if my y equal to say just closed interval 0, 1, then we say it is a lift of the path. Okay. Now the definition of covering space and definition of lift is both are clear to all of you. Yes.
Yes, sir.
Okay.
Sir,
Hmm.
we may use the term covering map for the map P.
Right. Right. You can say it is covering map. Fine. But anyway, we are not using here that map P. That is fine. Right. Now what we'll do? Now take one example. Now take the same example that x tilde and P as my R and that one which we defined, and my x is s1. Okay, that's mean P is okay. I can define cos 2 pi s comma sine 2 pi s. So this is my covering map P. Right. Now what we'll do? Okay. Now define say wn from 0, 1 to s1 this map. Say wn is equal to cos 2 pi ns comma sine 2 pi ns. Okay, so this is a path, right? Now this is a now wn is a loop which wind n times, right? So that's mean the situation is right. So this is my r, this is my s1, this is my p, and this is my 0, 1. Okay, this. Now can you tell me what will be the lifting of wn tilde? Tell me.
Zero one to R.
0, 1 to R. How to define?
S goes to NS.
The interval 0 to n. So like it will map fx equals nx or omega n tilde s equals n times s.
Right. It's a simple one. Because we need then P compose Wn tilde equal to Wn. You can check it is. So this is my condition. We need to satisfy. Now you can check. If we take Wn tilde s equal to ns, then you can check that this composition is actually Wn. See, because this is my P, this is my W, this is my Wn. Is that clear? So that's mean from now on you can say that when we want to prove that this is a fundament, that is what is the fundamental group of circle, then we will use this covering space and then we will have this covering map. Then you can see that this way you can, if we define, then Wn tilde is a lift of Wn. Is that clear to all of you?
Yes.
Okay. Now one simple thing. Now say Ws equal to this one, cos 2 pi s comma sine 2 pi s. So that's mean W is a loop from 0, 1 to S1, right? Now can you tell me what is W1 dot W, that is W dot W, that's mean that path product. Can you just quickly tell me what is that?
W2.
W2. So that is clear. Actually, now can you prove it by your definition of that product of path? So what is that actually? Now we know what is that. That was W2s, right? 0 less than equal to s less than equal to half, and W2s minus 1. So half less than equal to s less than equal to 1. Okay. Now what is W2s minus 1? What is that? Just put the value, cos 2 pi into, that is 2s minus 1, right? Now 2 pi 2s minus 2 pi comma sine 2 pi, again that is we have s, right? So 2s minus 2 pi, right? Now if we take minus here and then if you take, then it is actually cos, that is you can say 2 pi 2s, right? And if you take this one, you can take minus first outside, then it will be sine 2 pi minus something, again it is negative, so negative negative it will be positive, so it will be again sine 2 pi 2s. Is that fine? So therefore W product W, that is, if you write this, this is actually cos 2 pi 2s comma sine 2 pi 2s. Right? Now similarly, what is say W inverse or W bar S? Now we know that W bar S is W1 minus S, right? Now again, if you want to define W1 minus S, it will be cos 2 pi minus 1 minus S minus 2 pi S sine 2 pi minus 2 pi S. Right? So you can write it is as cos 2 pi minus S minus S comma sine 2 pi minus S. So therefore, is that clear? So therefore, you can just say that W this one power n is just my Wn, where Wn is cos 2 pi in S comma sine 2 pi in S is a map from 0 1 to circle. Right. Is that clear? It is just a product of parts. Yes.
Sir, can you explain the inverse of W, like W bar?
Huh. We know what is W bar. W bar is it is defined by W into 1 minus S, right? That is the by the definition. That is F inverse is actually F bar S, which is F of 1 minus S. That was the definition, right? Now I just put the values of 1 minus S. What is WS? WS is cos 2 pi S. Now it is 2 pi minus 2 pi S and sine 2 pi minus 2 pi S. That's when you can write it is this one only. Why you have actually doubt on this one? Why this is or this one? This final term.
Sir, I understand. Like I got confused in the computations.
Okay, now it is clear, right?
Yes.
Okay, and here this n from Z. Okay, it is not only for integer, it is Z because we can write here also you can find that minus 1 W power, right? Minus 1 means inverse. Okay, that is a simple one. And in terms of geometrically, you can say that if you have a circle, then W1 means it is round once, W2 means it is round twice, and W inverse means it is in backward direction, and W minus 2 means it is backward in twice direction. In this way, you can define Wn for n belongs to Z. Okay, fine. Now we prove one theorem. Any question? Okay. Now this theorem says for each path f 0 1 to x starting from a point say x naught, okay, and for each x naught tilde belongs to P inverse that x naught, there is a unique lift f tilde 0 1 to x starting from x naught tilde. Okay, but first read the theorem and just try to understand the statement. Because if you do not get the statement, then how will you approach, right? Now what is it is saying? Suppose you have any path. We are not okay. You can take loop as well, but because loop is a special type of path, but this is true for any path. Okay. So first of all, for each path f and starting from a point x0, that's mean f0 is x0. Okay. Are we using anything special about? No, that is fine with the path. Any right.
Range of f tilde is x.
Ah, good, good, good. Ah, okay. Now starting from this. Okay. Right. Now what is actually that this theorem says? Now can you tell me so what is actually the theorem says? The theorem actually says that you had one loop Wn, you had one loop Wn, right? 0 1 to S1. That was a loop, right? Okay, now one have to mute. Who is that? Okay. Now W1, what is Wn? Now Wn is a loop, right? And starting from the point 10 in S1, right? And we have seen Wn tilde 0 1 to R defined by that Wn tilde S equal to Ns. It is another path starting from 0, right? And this 0 actually belongs to that P inverse 1 0, right? Now this theorem says that lift is unique. That's mean if you have any lift f tilde 0 1 to R starting from 0, then f tilde will be same as Wn tilde. Okay, so that's mean this theorem served two purpose. One is it says whenever you have a path, it there is always existed another path lifting. That's mean any path has a lift. It says this one, and also says that that path that is that unique. Sorry, that lift is unique. Okay, so it says there is a path and that is unique. So here I use only that uniqueness part. That's mean we have that Wn is a path or loop in S1, and we have seen that Wn tilde is a lift of Wn. Now this theorem guarantee that Wn tilde is unique. That's mean if you have any lifting, this one starting from 0, then Wn tilde equal to f tilde. Is that clear to everyone? Yes?
Actually, sir, actually, sir, here we are taking that x not tildes from each evenly covered neighborhoods.
Which x not tilde?
That in the statement of the theorem means that if we have an x naught by
Hmm.
definition of of covering space and the covering that map P, that x naught will have a neighborhood U, and P inverse of U will be a disjoint union of U alphas.
Right, that is the definition of
Yeah.
covering
So
space.
and this means that in each copies of U alphas are homeomorphic to U by this map P restricted to U alpha.
Right, that is the definition.
So
Hmm.
and so this means that for that so that x naught has a copy in each x alpha. Sorry, in each U alpha.
Right.
And this x naught tilde is one of them.
If you take any element that should be in some U alpha, what does it matter?
Yeah. So now a lift means so f tilde from 0 1 to x bar. So means that we can separate that path because that x naught tilde is unique in this neighborhood. Say u alpha.
What are
Are
you
you
trying
getting
to say?
are you getting my point?
No.
Means
What are you
that
trying to say? So are you
means
saying that whenever you are taking, we are taking that x0, we cannot take any x0? Are you saying that?
no. I'm I'm uh, I'm trying to figure out the geometrical meaning of that statement. In
But
what
if
you
you
have.
take what, right, but this, if you look at that statement, but there is no, if you look at only the statement, there is no relation with that evenly covered neighborhood or something like that.
But once our P is this map means that x tilde comma P is a covering space, so that evenly covered neighborhood terms will automatically come, right?
No, that will not come automatically. It totally depends on the point x0. If you can choose any x0, depending on x0, you will get something something, and
Yeah.
for that something something, you will get a map. But ultimately, that map should not depends on the evenly covered neighborhood. If you can change even evenly covered neighborhood, still you will get that unique path. That path does not depend on the evenly covered neighborhood. And if you have a covering space, still that evenly covered neighborhood does not come automatically. It depends on the point.
Yes.
For the construction we will prove via covering that evenly covered neighborhood, but that does not make sense in that statements of the theorem. If you look into it is geometrically, still you do not need that the concept of that evenly covered neighborhood.
Okay. Thank you.
Right now, first of all, so anyone, can you tell me why we are saying that we have unique lift, and starting from x0 or starting from that 0 here in case. Now, if we remove that part, right, then can you say that this is unique?
No, like for every integer k, we can have a path from k to k plus n.
Right. So now can you give me another lift w till something, say f tilde?
Yeah, omega and tilde s is ns plus k for some fixed integer k. Like you
Right,
can take k equals 1, so n is plus 1.
right. So that's mean we can take then f tilde, say 0, 1 to r. We can take in this way that f tilde s equal to some k plus ns, right? And still p compose f tilde will be f. Can you see that? That's mean if we choose that f tilde equal to in this way, still it is a path lifting, right? But you can check that here when you choose that wn tilde, that 0 was 0 because that was ns, because that was a path lifting starting from 0, and this is also a path lifting, but it is starting from k. So that's mean so this is my 0, 1, 2, 3, minus 1, minus 2, minus 3, and this is your circle 1, 0. Okay. Now if this is your omega tilde, now omega 2 tilde s, actually this is this path that is starting from 0 and in that 1. Okay. Now if we take here k equal to say 4, then you can say k equal to 3, then you will get another path, this one starting from 3. So this is my f tilde. So that path will be different because their starting point and end point will be different, but both will be that w, that p compose f tilde will be again w2, and p compose w2 tilde equal to again w2, and f tilde is not equal to w2 delta. Okay, so therefore we need that part that it is starting from x0, that is starting from this. In fact, if we choose any point from f p inverse x0, that is a discrete set, right? And then we can always have a path starting from x0 tilde for any point choosing from this. But once we fix that point, then the lift will be unique. Okay, any question on in this? Yes. Is that fine? Yes or no?
Yes, sir.
Okay. Now we prove the theorem of this statement. Oh, sorry. We prove this one, but where shall I prove? I need proof. Now, first of all, what we have f is a function 0, 1 to x, right? And what we need to find? We need to find we wish to find ellipse f tilde from 0 1 to x tilde such that p compass f tilde equal to f. Okay, now what we use actually, since x tilde is a covering space. Okay, so we will use the concept of that. That's mean we will use the concept of the what you can say, we can use that concept of the evenly covered neighborhood. Okay, so first we use also here that 0 1 is compact. We use this as well. Now tell me, now just see, unmute and just speak. Okay, otherwise it will be, that proof will be very bold. So what is my f of 0? Where it is f of 0?
In X,
In x, right?
X naught with
It is actually x naught which is given and it is in x, right? And also we know that if every point in x has a evenly covered neighborhood, right? So now let u be an evenly covered neighborhood of x naught. Okay, then we know that x naught belongs to u, right? And what is my p inverse u? What is my p inverse u? We know that it is, tell me, what was the definition of evenly covered neighborhood?
Disjoint union of open sets.
Right, some disjoint union of u alpha, where p, if you take disjoint union of e alpha from u alpha to u, that is homeomorphism. Okay, fine. Now we, what we'll do, we now choose, right? Now that's mean if you take say p inverse x0. Okay, now p is inverse x0. What will be p inverse x0? It will be something kind of x alpha, where alpha belongs to that index set, right? Where x alpha belongs to u alpha for each alpha, right? So it is just a discrete set. Okay. Now instead we have many sets of this one. Now what we were writing that one, so we have not started the proof. We are just trying to visualize what is the thing actually. Okay. Now for this one, so it p inverse x0 has is a discrete set. It can be infinite, it can be finite, right? Now we choose say x0 tilde belongs to x. Sorry, belongs to x tilde such that belongs to say p inverse x0, which is subset of x tilde. Okay, we choose a point x naught tilde and we define say some f tilde 0 equal to x naught tilde. Okay, Now this way actually we define. So what we have? We have a map f from 0, 1 to x. Okay. And what we need to find? We need to find a f tilde from 0, 1 to x tilde such that this holds. Right? That's mean we have to define f tilde for all the points in 0, 1. Now we start with this. So we define f tilde at the point 0 as x naught tilde, which is given actually in the question. But how this x tilde comes? This is in this way. Now you should know that f in that is that collection of x naught tilde, it is a discrete sets. So if we change this one, then we will get a different f tilde. Okay, because that f tilde depends on the choice of x naught tilde. Okay, just we define this. Now we have to define f tilde for other points as well. But how to define that? Okay, now we use the compactness of closed interval 0, 1. Okay, so erase that. Right. Now again, f is a map from 0, 1 to x and p x tilde to x. It is a covering space. It is a covering map, you can say. Okay. And we have f of 0 equal to x naught. Now we wish to prove or find f tilde 0, 1 to x tilde such that p compose f tilde equal to f. So this is my x tilde, this is my x, this is my 0, 1, this is my f, p, and we need to find that. Okay. So let x naught tilde belongs to that p inverse x naught and define f naught 0 equal to x naught tilde. Okay, so this is the situation first of all. Okay, now we start the proof. Okay, now take any point t from closed interval 0, 1. Okay, now what is f of t? What is the range of f of t? It is belongs to where? X. Fine. Okay. Now let ut be an evenly covered neighborhood of f of t. Right? Because we choose first a point t here. Now t goes to f of t. And for this f of t, we take a open set ut. Okay. Now, since f is continuous, then f inverse ut is an open set containing t. Is that fine? Right?
Yes,
Yes,
sir.
sir.
Okay. Now this is a containing t. Now let a t be an open set and say interval such that t belongs to at and f of at subset of ut. Is that fine? And this is subset of 0, 1. Now open set in where? Open set in 0, 1. Open interval. Okay? Since it is an since f inverse ut an open set, right, and containing t, so therefore we have t belongs to some at subset of f inverse ut. So therefore f of ut subset of f of at subset of ut. So that is simple one. Now can you tell me why I am writing here at is an open set and interval, but I am not writing it is an open interval? Can you tell me why? Actually, you can write it is an open interval in the 0, 1, but that is an open set, but it does not looks like an interval, right? Open interval, because open interval means we generally follow this one. Is that fine? Because if you, when your t is 0, that interval will be of the form this sum epsilon. Okay, so I'm just writing here it is open set in this one and an interval. So that interval can be open interval, right? And it can be this kind of thing. Okay. Then that at t belongs to closed interval 0, 1 is an open cover of closed interval 0, 1. Now since closed interval 0, 1 is compact, therefore there exists a finite collection, say A0, A1, A2 up to AN, which covers 0, 1, and f of AI is contained in some evenly covered neighborhood of X. Is that clear? So what we did actually, we first take a t from 0, 1 and then ft belongs to X. Now we consider ut is an evenly covered neighborhood of ft. Right now, since f is continuous, so therefore f inverse ut is an open set containing t. So therefore we have t belongs to at subset of this. We generally take that open interval, but that interval can be this type as well. So we write it is an open set and interval. Okay. Now if we take only these types of intervals, and if we take vary t belongs to this, then it is an open cover of 0, 1. But we know that this is compact. Therefore we have a finite collection of this which covers 0, 1. And also it has the property that f of ai, right? We know that f of ai subset of some ut, right? So therefore it is contained in some evenly covered neighborhood of X. Okay, is that fine up to this? Yes or no?
Yes, sir.
Yes.
Okay. Now what does it mean? So that's mean actually we have this kind of set. So this is my 0, this is my 1. Okay. So you have say some this kind of open set. Say some 0, right? We have this kind of open sets. It is open intervals only, right? Which cover 0, 1. Now these are finite. So thus we have a partition say t0 less than t1 tn, which is 1, of closed interval 0, 1, such that how do we choose this partition? Say this is my t0. Now take this point here. Say this is t1. Say this is t2. Now say this is t3. Say this is t4 in this way, and this is my tn. Okay, so in this way we choose ti. So therefore we have a partition this such that f of ti, comma ti plus 1 contains in some ui, where ui is an evenly covered neighborhood in X. Is that fine with everyone?
So like how they are disjoint, like we took T0 to T1 T1 to T2 another, like the sets finite collection A0, A1, A2, AN, how they are disjoint.
No, no, they are not disjoint. They should not be
Then
disjoint, right?
how are we deciding T1, T2, T3, Tn? Well, T4?
Right. So this covers 0, 1, right?
I, yes,
These are
that
the
set.
these are the open these are the open sets. Open, remember that these are the open sets and they cover 0, 1. Okay. Now if suppose if you can say that no, it can 0 a0 can be whole 0, 1 interval, it can be fine. Then we have only t0 and tn. There will be nothing else. Now suppose you have two intervals which
So
cover
what
0,
are
1.
no, but like these TIs are initial points of AIs,
Sir,
or
sir, are you
No, no,
taking the endpoints of each intervals like TI?
no. We are not taking in endpoints. See, remember, see this one. We are taking that intersecting point. So there should be some intersection between since 0 close interval 0, 1. It is also connected. So there should be. If we first of all, if we take say one open set containing a0, 0. Or first of all, what you can take that since you have only finitely number of intervals, you can take initial points, and if you can make a order in terms of initial one, then each ai and aj will have an intersection. Can you see that? Because we have
I
only
mean
finite collection.
consecutive intervals will have some intersection.
Right.
Yes, because yeah, it's connected space, so you can't separate it
And
via two
right.
disjoint intervals.
And also main thing is we have only finite collections. That is important. Since we have finite collection, we have rearranged those easily.
Sir,
Because
then
this,
TIs are arbitrary?
yeah, it can be arbitrary, but we should take in that intersection only. That's mean if we take t say t I t1, that's mean t1 should be lie in the two intervals, not on only one. That's mean t1 will be in a1 as well as in a2.
Okay.
That is the reason we are taking that closed one. Okay, that is trivial. You just think we take this kind of interval. So whenever two intervals are intersecting, say this kind of one, say this is my one interval, say A0, B0. Okay. Now when you have another interval, it should not be lies from this one, right? It should contain the point B0, right? So therefore another interval should be from this way. And then we choose my T from here. Say Ti, whichever it is.
Like, how do we formally define this these set of points TIs? Like, uh, how do you define them formally in terms of a statement?
Right? If you want to write that one, you just try to find that. That is very simple. You first take one interval containing 0, okay, and say the endpoint is say that is A0. Now that endpoint, say that interval is 0 to some say B0. Then obviously will be another interval containing B0. Now take that interval and take that another right? So in that way you can define inductively. So take 0, say this one is 0 to say B0. You have one interval. Now B0 is not in that set, right? Now since B0 is not in this set, so therefore you need another open set containing B0. Say this one, say it is A1, B1. Now again, B1 it is not in this set. So therefore you need another some kind of thing, which is say C1, say A2, B2. In this way we can find, right? And then you can choose T from this way. So that you can write that f of this closed interval subset of some ui where ui is evenly covered neighborhood. Since we have finitely many points, finitely many intervals, it is easily done. Okay.
Okay, sir.
Anyway, you can think if you think that so this way it cannot be done, if you feel like this, then also you can think then to write it is formally, because that is not a difficult one. Okay, so that's mean f of t0 comma t1 subset of u0, right? Where t0 is my 0. Okay, now that's mean f of 0, which is x0, this belongs to u0 as well, right? Now let u0 p inverse of u0 equal to some disjoint union of u alpha, say. Okay. Now let u0 tilde be an open interval in x tilde such that f tilde 0 belongs to u naught tilde and p restricted over u naught tilde to u is an homeomorphism. Okay, now can you find in this way? So what is given that? Given f of t, f of this interval subset of u0. And what is my u0? u0 is an evenly covered neighborhood. That's when P inverse of u0 will be some disjoint union of open sets. Okay. Now since t0 is 0, so therefore f0 is in u0, right? And we also define that f tilde 0 is in x naught tilde. So therefore, out of these open intervals, there should be one open set, say u naught tilde, which contains the point f tilde 0. And this is an homeomorphism. Yes, this part is understood or not? Yes or no?
Yes, fine.
Okay. Now, can you guess now what should be the definition of now f tilde? Now we define f tilde on the interval t0, t1 by just, since this is an homeomorphism, so P that inverse compose F. So thus you can say that P compose F tilde equal to F on the interval t0, t1. Okay, so we
So
define, huh?
how can we say u not tilde is an open interval in X tilde? Like,
No, no,
shouldn't it
that,
be open set?
oh, sorry. Thanks. Thank you. Okay, now is that part clear to everyone? Now what we had actually, so we knew that f not tilde is defined at the point 0. Okay, and we know that f of this closed interval 0 comma t1, it is in u0, and u0 is an evenly covered neighborhood in x. So therefore, since f not tilde 0 is defined, was defined, so therefore we know that if so one, at least one interval from this u alpha, say u naught tilde, that is an open set in x tilde, right, which will contains that f tilde 0, right? And we took only those one, that is those interval u naught tilde, and this is a homeomorphism. So now we define f tilde on the whole interval, that is t0 to t1 by this. So in this way we define, so therefore you can check that P compose F tilde equal to F on this interval. Is that fine? Right? So you can say that thus now F and F tilde both are defined at the point T1. Okay? Now we move again, we repeat this same argument. Now we repeat from this argument. Now again F of T1, T2, that is subset of U1. And we know that U1 is an evenly covered neighborhood. Okay, so that's mean f of T1 belongs to U1. And we knew this point, f tilde T1. Okay. Now let U1 tilde be an open set in X tilde since it is an evenly covered neighborhood such that F tilde T1, since it was defined from before, right, from the last portion, it belongs to U1 tilde, and P compose U1 tilde from U1 tilde to U1 is a homeomorphism. Now we define P compose, we define F tilde on T1 comma T2 by the same formula. So this, since it is an homeomorphism F, so thus P compose P tilde equal to F on, we know that T0 to T1 union T1 to T2 as well. So therefore T0 to T2. Okay, is that clear? Now again we can repeat. Now we know F tilde T2. Now again proceeding similar approach, right? So after finite number of steps, we can define F tilde on say Tn minus 1 comma Tn, which is 1, by that P inverse U n minus 1 compose F. So that is P compose F on the union equal to T0 comma Tn, that is on 0 1. Okay. So in this way we can construct the F tilde. Now any question do you have? So did you understand the proof first of all? That proof is not difficult one. This is just by using some simple arguments. Okay. So in this way we can define the lift of a function, and then we have to show that that lift actually the way, if you take any lift of f, so we are giving here the existence of lift, and actually the way we have defined it, it will be unique as well. So in the next lecture maybe we will prove that is unique, right? And then we can prove the fundamental group of circle is Z. Okay, so any question? Yes or no? Hello?
Yes, sir.
No question.
Okay, then we can stop today then.
Yes.